Next up, we'll have our seminar on Bayesian spatiotemporal modeling of passenger trip assignment in metro networks by Xiaoxu Chen. Xiaoxu is a postdoc here in HEC Montréal and has his PhD from University McGill. Montréal for a little while already, quite familiar with the house. Yes, thank you very much for presenting your seminar, Xiaoxu. You're welcome.
Okay, hello everyone. I'm Xiaoxu Chen, and today I will talk about the paper. This is about Bayesian spatiotemporal modeling of passenger trip assignment in metro networks. And this paper collaborated with Dr. Alex Smith and Dr. Zhengliang Ma and Dr. Li Junsun. Okay, before introducing the research problem and the methodology, let me first introduce the AFC data in metro systems. Actually, AFC is automatic fare collection systems. These type of systems are widely used in metro systems. And in this type of systems, passengers are required to swipe their cards or mobile phones when they enter the metro systems or leave the metro systems. So from this type of systems, we can collect the detailed information of passenger trips. For each passenger trip, we can collect the trip ID and the origin station and destination station and the tap-in time and tap-out time. Then I will introduce what is passenger trip assignment in metro networks. Actually, in metro networks, the passenger trip assignment is try to determine the specific passes passenger take from origin to destination with the metro network. For example, in this figure, here is the metro network, and from the origin to the destination, there are two alternative passes. And well, from the AFC data, we can easily to collect the OD flow. We can know how many passengers traveling from this station to this station, but we do not know how many passengers traveling over this path or this path. So the passenger trip assignment in metro network try to determine the passes that passenger take. And the passenger trip assignment results are very important for metro systems management and operations, such as the network design, train scheduling, and fare policy. So as we said, the AFC data, we can get the trip ID, origin station, destination station, tap-in time, and tap-out time, but we do not observe the passenger passes. So in this talk, we focus on how to infer passenger passes using AFC data. Okay, then let me introduce some notations for the problem formulation. For any origin destination pair, the OD pair, there exists a set of feasible passes. And when multiple passes exist, then passengers choose a path based on various factors. So actually, here we'll concern about passenger path choice model. And our observed AFC data, actually from AFC data, we can calculate the trip travel time for each trip. So we can get the set of trip travel times. Then each observation is the travel time for trip M between the OD pair, and we can also know the starting time interval. And the objective is to infer the latent path choice for each trip observation. Then we need here we try to develop model for trip travel time. To model the observed trip travel time, actually based on the physical meaning, we can decompose the trip travel time into four components. the access time, in-vehicle time, transfer time, and egress time. Here I use this figure to how the components construct the trip travel time. For example, if when a passenger tap in, then the passenger will wait for the passenger will go to the platform to wait the train, and when the passenger board the train, this duration is the access time. When a passenger board the first train and goes through some links and then alights the train, here the duration is the in-vehicle time. And when the passenger alights the train and then walking to another platform or wait at the same platform until the passenger boards the next train, here is the transfer time. And another train, there are also another in-vehicle time. And when the passenger alights the final train and tap out, then we can there is the egress time. So actually, for each observation, for each observed trip travel time, we can decompose them into these 4 components. Because later we will consider the choice model. So here we use the word cost to represent the travel time. And we can represent the cost associated with these components. We can get the access cost and the vehicle cost and transfer cost and egress cost. And then we can combine our type of cost into a single network cost vector. And we consider the network dynamics. So we try to, here we define a sequence of time varying cost vector. Okay, then if we have a given path choice, that means for a given path, then the observed travel time can be expressed as a linear combination of the network cost. And in this function, the matrix A is a binary routine matrix. That means within the network for any origin to destination for any path, we can construct a binary routine matrix. So for the trip travel time, we can build the linear function with the network cost. And the optional is a zero mean error term. Actually, this problem is very challenging because it's an inverse problem. We only observe the trip travel time, but we do not observe the network cost. We do not observe the path choices. So we need to estimate these latent variables from the observed trip travel times. Then the next question is for the linear model, how to model the error term. Actually, a simple assumption that we can assume all trip travel times have the same Gaussian noise. But actually, it's unrealistic because for different passes, for example, the longer passes or more complicated passes could have larger variance. So to capture the heterogeneity in different passes, we can model the variance of the error term for passes as being proportional to the passes expected cost components. So here we can define the error term with the binary routine matrix that can build the variance, the errors with the network cost and the path, the binary metric routine matrix. While we can use the user theta, the coefficient of variation vector to capture the heterogeneity among different passes, but still the dimension of the theta is still high. So to reduce the parameters, here we assume a common coefficient for different type of costs. For example, for the access cost, we can use the same coefficient of variation, and also for the in-vehicle cost and the transfer cost and egress cost. Then finally, we can get the observation equation. Then to model the dynamic of network cost, here we model the evolution of the network cost vector using random walk. Then here I will introduce the path choice model. Actually, the multinomial logit model has been widely used for passenger choice behavior in metro networks and in transportation networks. And previous studies often assume the passenger choice behavior, they have the same utility parameters. They do not consider the spatial temporal variations. Actually, passengers' choice preference should not be static. It should consider spatial temporal variation. Here, in the multinomial logit model, the utility usually defined as a linear combination. In metro network, metro systems, it's usually defined the linear combination of the in-vehicle cost and transfer cost. So here is a utility function, and this part is the sum of the in-vehicle cost, and the second part is the sum of the transfer cost. And these parameters theta and beta, they are special temporal varying coefficients for in-vehicle and transfer cost. And then from it's a standard multinomial logit choice model, we can get the choice probability. Okay.
There's no error term in there in the utility function, but I don't see it.
Is this one?
Yeah.
Yeah. Actually, this is a utility. Yeah, and yeah. So what's your question?
There should be an error term, right? Oh,
yeah.
Estimate.
I understand. Yeah. Actually, utility function is here is the error term, and usually we assume the error term is a Gumbel distribution, and here is like the I don't remember the exact term. But if we assume the error term is a Gumbel, and then we can get this equation. Yeah. Okay. Then these coefficients are very high dimensional. Actually, there are some spatial temporal correlations. So to model the spatial temporal correlations, a natural method is to impose the Gaussian process prior or the lead parameters. But this type of parametrization has the problem in this problem is the dimension is very high. So to estimate the parameters is very it will need a huge computation to achieve the convergence. So to reduce the high the dimension, we represent the coefficient into a tensor, parameter tensor, and we use the tensor decomposition to reduce the parameter. And also to consider the spatial temporal correlations among the coefficients, we also use the Gaussian priors or the tensor factors. And for this one, we impose the spatial correlation, and for this one we impose the temporal correlation. And for the factor matrix U, there are different type of coefficients. Here we also impose the Gaussian prior, and for the covariance we impose the inverse V-short prior. Then we can get the analytical posterior for the covariance. Yeah.
You go to the previous slide. I don't see where they appear. This VR, WR, and KU. I couldn't follow where
okay,
they appear, right?
Okay, sorry. Yeah, it's
okay.
From here. Yeah.
Okay, you have made this kind of a
decomposition. Yeah, because we have the dimensional tensor, 3-order tensor. The first order is the first order sorry, I think the next page is wrong. Yeah, it's incorrect. Yeah, UR is represents the two different type of coefficients, right? The in-vehicle cost and the transfer cost. And actually, VR should be the spatial, yeah, and WR is the temporal dimension. Yeah, I think. Oh, yeah, correct, actually. Yeah, this is the spatial dimension. So we impose the spatial correlation and the temporal. And for different type of coefficients, they could have also correlation. So here because we do not know the exact correlation, so we impose a function prior with the covariance KU. And we also impose the prior or the KU, so we can estimate the KU. And to infer the model parameters, we developed the Markov chain Monte Carlo sampling method. It's a standard method to estimate the parameters of the model. Okay, then let me introduce the experiments. First, we do the simulation study. Here we use the network topology from the Hong Kong MTR system, and we generate a cynetic data set by setting a set of ground truth parameters. That means we assume some ground truth parameter, then generate the data set. We can get the trip travel time observations, and then we use a type of data to infer the parameters, to recover parameters. So the simulation study try to validate whether our inference method can recover the parameters. Okay, here this figure presents the recovery of some simulation parameters. And the first row are some parameters of mean cost, and the second row are some parameters of in-vehicle coefficient, and the last row are the some parameters of transfer coefficient. And the red line are the estimated mean, and the blue line are the true value, and the pink area are 95 credible intervals. Overall, we can see our developed inference method can recover the parameter very well. And this figure also try to present the recovery of spatiotemporal choice coefficients. And it also proved that our inference method works. And then we apply our method or the real world data, and we use the AFC data from Hong Kong, and we select a typical weekday, and there are more than 4 million passenger trips, and we use the data to estimate the parameters of the model. here is the estimated posterior mean and 95 credible interval of spatial temporal coefficients. It's for the in-vivo coefficients. And overall, we can see these coefficients are spatially varying. While in this figure, it's not very clear for the varying over time, but actually they did. Yeah, actually in this figure currently we didn't present the some curves over time, but in the revision we try to present them. And this figure also presents the estimated spatial temporal coefficient for transfer cost. And here we also present the estimated link and access cost in metro networks. And there are some estimated egress costs in metro networks, and also the estimated coefficient of variation parameter for networks. And this figure presents the final passenger flow assignment. The first column are the posterior means, and the second are the standard deviation. And actually, the passenger trip assignment tried to get the final results of these figures. We can know how many passengers or its link, right? And the results are important for transit agency to make network design or operation optimization. And we also here present some some OD pairs, the temporal variation of path choice probabilities. Overall, we can see for the OD pairs, the path choice probabilities are vary over time. Okay. Yeah, here I would like to introduce a very useful application of our model. If we want to build build a new metro line, and we need to consider when the new metro line is built, how the passenger flow distribute. Actually, in our model, we have give a good estimation of the choice model, the spatial temporal choice model. So if we choose a new line, we can actually use the Gaussian process to estimate the path choice probability for new stations. Then we can actually, after we forecast the OD demand, then we can distribute them all the network. Okay, then in summary, in this work, we propose a Bayesian framework that can estimate the network cost and the path choice, and we propose the spatial temporal multinomial logic choice model. And we also developed the inference method, which is very useful. Okay, that's all. Thank you.